Hello and welcome to Lapping Analytics. My name is Jimmy Lapping. I'm a psychologist and statistician with an interest in a range of topics, including research methods. On my channel, I have shared quite a few videos on research methods already, including binary logistic regression and qualitative comparative analysis, although those two methods have always presented in separate videos on my channel. So I thought I should also provide an example of a data set on which you can apply both methods. Because in the videos thus far where I presented qualitative comparative analysis, I showed examples of very small sample sizes, which actually are too small for logistic regression. But here I have a data set which is large enough to apply both methods, because qualitative comparative analysis can be applied to smaller and larger data sets. But here this data set is also big enough for logistic regression. So I'm going to show this example in this video to show how these two different methods compare and why they can be used in combination because they provide complementary insights into your data. So here we have a simulated data set, which shows a total of 256 participants, 4 times 64. So we have 4 possible cells, and these 4 possible cells are all possible combinations of the presence 1 or absence 0 of treatments x1 and or x2. And participants were actually allocated randomly to these cells. So this is a randomized controlled experiment. A balanced design, so x1 and x2 are uncorrelated in this example at the design level. So there are 64 participants that formed the control group because they had no intervention whatsoever, neither x1 nor x2. Then there were 64 participants that received only x2, another 64 participants that received only x1, and finally another 64 participants receiving both x1 and x2. The column on the left is a sum because it's the number of participants that received a success rating on the dependent variable. The dependent variable was a binary variable here, with 0 being failure and 1 being success. So there are 12 success cases in the control group, 31 success cases for the participants that received only x2, 43 successes for the participants that received only x1, and a total of 55 successes for the participants that received both treatments. There are several methods that you can use to analyze this data, also several ways to visualize the findings. Here we have an example of a plot indicating the probabilities of success for each of 4 possible cells resulting from a binary logistic regression model with interaction term. And what I'm going to show now is the information criteria AIC and BIC and the R-square McFadden for each of 5 possible models. I will explain them in a bit more detail. So first of all, in the model column, you see the first row starts with null. That's the null model, which basically indicates that it does not matter whether you receive x1, x2, both, or no treatment. In the end, the chance of success is the same. Then we have a second model which says x1, which means that the presence or absence of x1 makes a difference in terms of the chance of success. Model x2, which states that x2 makes a difference for the chance of success. Then x1, x2, that's the main effects only model, which indicates basically that x1 and x2 have additive effects, and this is on the log odds scale. When you write out the logistic regression equation in log odds terms, then x1 and x2 have additive effects, meaning they have parallel regression lines on the log odds scale. And the last model also includes an interaction term, which means that on the log odds scale, the regression lines don't go parallel. Now, AIC or Akaikis information criterion and BIC or Schwartz Bayesian information criterion are frequently used information criteria. There are plenty more, but I'm showing AIC and BIC because they are used quite frequently, and both can be used as follows. Although a value for a specific model is not really useful, you can compare different models in terms of these criteria, such that the model, so provided that all models are applied on the same data set, which is the case here, you can say that the model with the lowest value on the criterion is the best model, or is the model to be preferred. The R-squared statistic is actually a statistic which actually is higher when the model performs better. So the first model, the null model, has an R-squared of 0. Then X1 has an R-squared of 0.14. X2 has an R-squared of 0.044, which is notably lower, and that's why you see, for instance, that AIC and BIC of the X2 model are higher than for the X1 model, because AIC and BIC actually work the other way around. The lower, the better. So what AIC and BIC basically do is, okay, we compare different models. So for instance, you can also have a look at x1 and x1 comma x2. So the R-square statistic is 0.195 instead of 0.14. So the R-square goes up. And you also see that the AIC and BIC are lower for the x1 comma x2, so the main effects model. Um, and actually, of these 5 models, the best model is the main effects model. Because for the interaction model, so we add one term, which is the product term, which means that on the log odds scale, the lines don't go parallel. You see that the R-square statistic on 3 decimals still remains 0.195. So it's no surprise that AIC and BIC are higher for the interaction model, because we have added complexity, but that added complexity does not translate in a substantial improvement in performance. So in this case, AIC and BIC indicate that the main effects only model is to be preferred. On the log odds scale, parallel regression lines. So this is binary logistic regression. We can also use qualitative comparative analysis on this data set, which actually is a method that gives, among others, 2 statistics, consistency and coverage, and it can do that for different terms and for combinations, depending on whether the final solution consists of one rule or several. So for instance, in here you see where it says model, I might as well actually say rule, because the first row lists x1. So basically that states that, so basically this looks at the consistency and coverage of x1. What is that? Well, there are a total of 64 plus 64, or 128 cases that received x1. The question for consistency is, how many of those 128 cases actually result in a success? Well, we have 43 successes for the combination x1 yes and x2 no, and we have another 55 successes for both x1 and x2. So that means that we have 98 divided by 128, and that's the 0.766 consistency, which means that in just over 3/4 of the cases where a participant receives x1, there is a success. Still, 23.4% exception. They don't result in a success, so quite some exceptions to the rule. the coverage is 0.695. Why? Well, the coverage is about how many of the success cases can be explained by x1, or literally are covered by x1. So there are 12 plus 31 plus 43 plus 55 successes. Those we need to add. So we have a total of 43 plus 43 is 86 plus 55 is 141. That's the total number of successes. How many of those are from x1? Well, that's the 43 plus 55. So it's the 98 divided by 141. That explains why the number of successes. So in this case, the coverage for x1 is 0.695. So almost 70% of the success cases are covered by x1. For x2, we see that the numbers are slightly worse. We see that both the consistency and the coverage go down because the effect of x2 is less pronounced than that of x1. You also see that in the output of logistic regression, right? You see that for the R squared for x1 is 0.14, while that for x2 is 0.044. So that means a weaker effect of x2, and that also results in lower consistency and coverage values in this randomized controlled experiment for x2. And then there is another line which says x1 and x2, because yes, there are a total of 64 cases that that received both x1 and x2, and 55 of those had a success. Hence, a consistency of 0.859, almost 86%. So there are considerably fewer exceptions to the rule here than for just x1. So based on consistency, this would be a better model. Now, what is a little bit of an issue is that the coverage, of course, is lower here, which is in a randomized controlled experiment isn't necessarily strange, because of course we partitioned the total data set in 4 equally large cells. So unless we have very few successes outside the 1-1 combination, it's very difficult to get a high coverage value, but it does indicate that of all the successes, 39% are in the x1 and x2 group, which is basically the 55 successes in that cell divided by the sum of successes, which was 141. So hence 39% or 0.39 as coverage. Purely in terms of consistency, you might actually, when we look at coverage, you might say that x1 is the better model because more cases are covered by x1. However, the consistency is also somewhat lower, and well, there is you cannot really say there is a consistency value which is always good. Starting this point, it's always great, and lower than that, it's always bad. But often values of 0.8 and higher are considered decent consistency values. And in this case, so based on consistency, you would say that the solution of x1 and x2 performs better. But of course, keep in mind the coverage will be lower. It is the only solution that results in a consistency of 0.859, but the coverage is lower. Now there is another solution that you can look at, which is x1 or x2, which is basically saying that okay, so it's x1 or x2 or both technically, yes. And then you can say that there is a consistency of 0.672. Why is that? Because there are a total of 64 plus 64 plus 64. So that's 192 cases where either x1 or x2 or both were present. And how many of those resulted in success? Well, 31 plus 43 plus 55. You divide that latter sum by the 192 and you get 0.67 as a consistency. So actually the same as what we got for x2. Yet you see in this case the coverage is much higher because, well, there are 141 successes. Well, right, that's the sum of the successes, and so actually the sum of the left column in the small table. That was 141 cases, and a total of 129 of them are actually from participants that received at least one treatment, so either X1 or X2 or both. So the coverage goes up. There are only 12 successes which are not covered, so just over 8% of successes not covered by the rule X1 or X2. Coverage up, but consistency down, and lower consistency values are generally not recommendable because basically it means lower consistency, more exceptions. It's a weaker rule. So here, if we take the criterion of a consistency of at least 0.8 as an outcome, well, in that case you would prefer the x1 and x2 instead of the x1 or x2 rule. So that's how these two different methods stack up. Of course, this is a very simple data set with only two variables in a randomized controlled experiment. Of course, in many real-life studies, which are not randomized controlled experiments, you will have you will probably not have a balanced design. So you will have some correlation between x1 and x2 as well. You may have more variables as well. But okay, I wanted to show these two methods using a very simple example on purpose with just two independent variables to basically show how they compare and actually that both of them can provide useful information. It's perfectly possible to use both methods and to also report the outcomes of both methods in a paper because they shed light on the same data from a different angle. Well, I hope you found this useful. If you have any questions, any comments, any suggestions for future videos, just leave a comment below this video. Thank you for watching, thank you for listening, and I hope to see you soon on this channel again. Bye bye.